Everyone, long time no speak. I thought instead of making you watch an Ed puzzle today, I would just kind of do the notes myself. So here's the thing. Heating curves are a way we keep track of phase changes from solids, liquids to gases, and what happens to the temperatures as we monitor them. So identifying what states of matter, what energy changes, and what phase changes are occurring on a heating curve. We're also going to potentially add cooling curves as well. Now, a cooling curve is literally a heating curve reversed, so just flipped over. We'll see that in a little bit. First things first, the phase changes you need to know. Boiling and condensation. So that's boiling is liquid to gas, condensation is gas to liquid. The boiling condensation point are specifically the temperatures that this phase change occurs. Now, for something like water, it's 100 degrees Celsius. You heat water up to 100, it boils. You cool steam down to 100, it condenses. Freezing and melting points, same thing. The temperature at which a liquid changes to a solid or a solid back to a liquid. Key thing, the points are the temperatures. So at 0 degrees Celsius, water can exist as liquid or ice as a solid. So you heat ice up to 0, it melts. You cool water down to 0, it freezes. But either way, it's at 0 degrees. Evaporation is one of those phase changes that gets confused with boiling a lot. Evaporation is when the liquid turns into a gas below the boiling point. Evaporation can occur at any temperature that a liquid is a liquid. Boiling specifically has to be at the unique boiling point for that substance. Water only boils when you get it to around 100 degrees Celsius, depending on altitude. Water can evaporate at any temperature. It's just random molecules escaping from the liquid into gas form. I didn't mention too much about these two over here, sublimation, deposition. We don't see them very often. That's when the liquid state is totally skipped. That's when a solid turns directly into gas or gas deposits directly back into solid form. We see this with something like carbon dioxide. It's a gas normally, but if you've ever heard of dry ice, that's solid carbon dioxide. It's not frozen because freezing is liquid to solid. It's deposited carbon dioxide. It went from gas directly to solid. And dry ice is called dry because as it heats up, it doesn't get wet, it doesn't liquefy, it goes directly to the gas state. Now, a couple different types of energy that you need to know about. There's kinetic energy, there's potential energy. When we talk kinetic energy, it's always the energy of motion. And we represent that in this case by the temperature. Temperature is defined as the average kinetic energy of a substance. If something is hot, it has high kinetic energy. If something is cold, it has low kinetic energy. The higher the temperature, the more kinetic energy something has, the faster it moves. Contrary to this is potential energy, the energy of position. So potential energy, a way to think about it is if you have a ball sitting on a table, it has very low potential energy. But the higher you lift it, the more you change its position from that table, the more potential energy it has. And that potential energy can be released by letting it go and letting it fall. So when we talk about potential energy with respect to states of matter, we're talking about the energy involved in phase changes, specifically when we spread molecules apart or bring them back together, depending on whether we're heating them or cooling them. Do not confuse heat and temperature. They are two different things. Heat is just energy. Temperature is specifically measuring kinetic energy, how fast things are moving. If you aren't changing the temperature, you're not changing the speed. So at a specific phase change, doesn't matter which one, at any of them, the temperature is always constant. At phase changes, you're not making things move faster or slower. We're not changing the kinetic energy. We are changing the potential energy. And this should say potential. Sorry about the typo. I don't want to re-record all this. So at phase changes, particles are spreading out or coming together, they're changing their position only. You can only change kinetic energy when you have one phase, one state of matter. Whenever you have a constant temperature, that's a phase change. The way we remember that, the 6 P's of chemistry. At a phase change, particles change position, which changes potential energy. We find those on the flat, get it, flat lines of heating curves, and they're always representing a physical change, meaning it's the exact same substance, exact same formula before the phase change and after. So particles change their position at a phase change, it's potential energy, it's physical, and it's always on the flat lines. Now I'm going a little fast. You can always rewind or use, the speed controls to slow me down. I don't want to make this too terribly long of a video. Now, your typical heating curve looks like this, where we've got heat down here and we've got temperature here. This is not water's heating curve. We know it's not water because the flat lines for the phase changes are occurring at -60 and +60 degrees. If this were water, this bottom one would have to be 0 and this top one would have to be 100. So this isn't water. Now, at really, really cold temperatures, you have solid only. That means the molecules are just vibrating in place. And as you add energy, they vibrate more and more and more. So their vibrations increase. That's a change of kinetic energy. So they're actually vibrating faster and faster until they vibrate fast enough that we can disrupt some of the intermolecular forces. That's when we have our first phase change. And that's when the solid starts to melt. Now, melting, you end up having both solid and liquid present. I'm going to come back to that in a little bit. Solid and liquid present as the molecules are vibrating themselves apart. It is potential energy because they're vibrating at the same speed that they're moving. They're just breaking apart from each other. We're overcoming intermolecular forces. Instead of everything being stuck together, they start sliding past each other. As soon as the last molecules have uncoupled, the temperature can start to rise again. And that's when we have liquid only. When we have just liquid, again, we have molecules that are sliding past each other, still in contact. This is a temperature change during this area, so this is also kinetic energy. And the hotter you make it, the faster those molecules move. They're still in contact, they're still slipping and sliding past each other, but they're moving faster and faster and faster until we get to the point where they're moving so fast that they can break apart. And that's where boiling comes into play. Boiling occurs when the molecules are now moving fast enough that the liquid is turning into a gas. Now, this means the molecules are changing their position again, so it's potential energy. The liquid molecules are separating, and while they were moving really fast but touching, they're now moving really fast but not touching anymore. And all the energy that's put in here is used to disrupt intermolecular forces. This potential energy is breaking intermolecular forces. Once the last molecules have uncoupled, then you go back to just having gas only. We're moving fast, moving in lines. We're widely separated, and you can start raising the temperature again. So it's a change in kinetic energy. Now, common questions that get asked. If I were to ask you, where on this heating curve would you find a liquid? You might be tempted to just say, oh, liquid is right there. And that's true. But you would get that wrong on a test because you missed the liquid that was right there. You'd also miss the liquid that was right there. Beware of questions that say, where is liquid versus where is only liquid? Where is there only gas? Right there. If I ask, where is there gas? It's there and there. If I ask you, where is kinetic energy changing? That is anywhere the temperature changes. If I ask you, where's potential energy changing? That's anywhere you've got the flat line. Remember your 6 P's. If I asked you, what's the boiling point? That's your 60 degrees. Your melting point is your negative 60. Now, if we go heat removed, the same thing happens. We go starting at high temperature, so we start with a gas, then we have a gas becoming a liquid, then only liquid, liquid becoming solid, and then solid only. I've literally just flipped the curve around. This is called a cooling curve. Again, kinetic energy, kinetic energy, kinetic energy, potential energy, potential energy. Temperature change, kinetic. Temperature's constant, potential. That's it. These are not meant to be incredibly difficult. So at this point, we are going to stop recording. We're just under 12 minutes, and you'll get a chance to practice with some homework on this tonight. If you have any questions, shoot me a message on Google Hangouts, and if I'm available, I can hop on and show you stuff on your screen if need be. Have a good day.